Hi there, we're doing CCEA AS Physics from June 2015, and this is Unit 2 of that course. Question 1a, Figure 1.1 shows part of the electromagnetic spectrum. Complete Figure 1.1 to show the missing regions of the spectrum in the correct order. So we're starting down here with a radio and working our way up to gamma. So this is like long wavelength or low frequency, and this is short wavelength or high frequency. And this is just straight learning book work. We obviously have visible light in the middle, and then we need to establish what is either side of that. Important to recognize that the sort of dangerous stuff is the high frequency stuff towards this end. So gamma rays are preceded by, in this zone, X-rays, and X-rays are preceded by ultraviolet. So we've got visible in the middle, UV, X-rays. Now we have UV just beyond visible. So below visible, below the red, we have infrared. And that leaves only microwave to go in the gap here. And that's the way you should sort of think about these things. You either learn them off in a sequence, or you think about sort of, the way I do it is the level of danger is going up in this direction. So then we have a basic wave equation question. A local radio station broadcasts at 94.5 megahertz. Calculate the wavelength at which this station broadcasts. So we need speed of light from the data sheet. So V equals F lambda, and lambda then equals V over F. So we've got speed of light on the top line, 3 times 10 to the 8, 94.5 mega on the bottom. And we divide those and we get 3.17 meters. Part C then says state 3 differences between an electromagnetic wave and a sound wave. So probably just break this into a little table, just so that you can compare the properties. So the first and most obvious is that electromagnetics are transverse and sound is longitudinal. Transverse waves obviously then have the ability to be polarized because their vibration is perpendicular to the wave direction. Longitudinal waves can't have polarization because their direction of vibration is already aligned with the direction of propagation. And then obviously the unique property that electromagnetics have, that they can travel in a vacuum. And sound is a mechanical wave, it needs a substance to travel in, so sound cannot travel in a vacuum. So electromagnetics don't require a medium, but sound does. Question 2a, a ray of light is directed through water towards air at an angle of incidence of 0 degrees at the surface. Describe what happens to the ray of light after reaching the surface of the water as the angle of incidence is increased from 0 degrees towards 90 degrees. So this is done in sort of stages. Really, we start with this example where the angle of incidence is 0. And remember, the light is leaving from the water into the air. And what we get here is no bending. The light just comes straight out of the surface, and so the angle of refraction is also 0. So as we start then to increase this angle of incidence, we notice that the refracted ray bends away from the normal. Remember, it'll always bend away from the normal in the region that is the faster speed of light. So the speed of light in water is lower, higher out here, so it bends away from the normal. So when we get to this value that's still less than the critical angle, we get this behavior. And then finally we get to the point here where the angle of incidence equals the critical angle, just here. and that results in the angle of refraction here being 90 degrees and the ray just shooting along the surface like this. So no bending, bending away, bending so much until we reach 90 degrees. And when we reach this case of 90 degrees, we're at critical angle. And then finally you get to this last case where you have I greater than C and you get total internal reflection because we've got I greater than the critical angle in here. So no light leaves now, we just get reflection. So you've really just got to go through these four cases. I equal to 0, R equal to 0. I has a value, R is greater, so it's bending away from the normal. I reaches the critical angle, you get this refraction of 90 degrees, and I beyond the critical angle, you get total internal reflection. Part B1, as a ray of light travelling from air enters the cornea of the eye, it is refracted as shown. This is to allow the light to be focused on the retina. So we've got the cornea on this side, air on this side, and the refraction is going on as it crosses this boundary. So this is a nice straightforward case of using Snell's law. We've got, we're in air here, we've got an angle of incidence, we're in the cornea here and we've got an angle of refraction, and we're asked to show that the refractive index of the cornea is going to be 1.4 to 2 significant figures. So we're just filling in the equation for Snell's law. Right, so we have our Snell's law equation to fill in. So sin I over sin R equals n. And so we have sine of 34 over the sine of 24 equals n. And that comes out to be 1.37, which is 1.4 to 2 significant figures, which is what we were asked for. Just be careful about your calculator being in degree mode when you start taking sines of angles. Part 2, water has a refractive index of 1.3. With reference to your answer in B1, explain why images are not focused when your eyes are open underwater. So what's going on here is that the refractive index of water is too close to the value of the cornea, and that means there's not enough difference between them to get a good amount of refraction. So the refraction will be too weak, and that means that the image will not form. Basically, if you think about the system, you're trying to take an object and focus it somewhere on the back of your retina. So you want this kind of thing to happen. If the refraction is too weak, say for these blue rays here, weaker amounts of refraction will lead to them not forming a sharp image at your retina. So I've just said that the refraction would be too weak to focus an image because the refractive indices are too similar. Question 3. A student carried out an experiment to measure the focal length of a converging lens using the apparatus shown. So we've got a filament bulb, a lens and a screen. The student measured the image distance V for 3 different object distances U, and the measurements are recorded and shown in the table. Describe how the image was located and the image distance measured. So what's happening here is that we set up this object distance, say for example to 15, and then we move this screen back and forward until we see a sharp image of this bulb. And when we see a sharp image of the bulb on the screen, we're at the focused image distance. And then we change the U, move this bulb, set a new object distance, and move the screen again and find a new image distance. So what's happening here is that when we had the filament bulb here 15 centimeters from the lens, we found that the screen had to be 32.2 centimeters out. When we moved this to 30 centimeters from the lens, we found that the screen had to be 15.7 centimeters from the lens. And when we moved the image distance to 40, we found that the screen only had to be 13.8 centimeters. So you set this up, and then you move this screen until you see a sharp image, and then you measure out the image distance. And so that's what you're explaining. So once we get a sharp image, we measure the image distance V here from the screen to the center of the lens. And obviously you should mention using a meter stick or something for that. So you might want to draw in a meter stick. Okay? Okay, so part 2 then. If the object used was 5 centimeters in height, what is the minimum height of the screen required to display the images produced? So if you remember that the magnification in a system is the height of the image over the height of the object, and that also relates to the image distance over the object distance, then we just need to look at the numbers where V was much greater than U, the case where the ratio of V to U was greatest. Now we look back at the numbers. V to U is greatest in the first set here, 32.2 over 15. It's smaller in all these cases, so that's the pair that we're interested in. That'll give us the biggest image, and that'll tell us what size of a screen we're going to need. So we need to fill that in. So the height of our image will equal V over U times the height of the object, so we just sub into that. And the worst case was 32.2 over 15, and we multiply that then by 5, and that gives us 10.73 with the 3's repeating. And that's in centimeters because this was in centimeters. Part B then says use all of the data in the table to calculate an accurate value for the focal length of the lens. So that means you're going to calculate using your lens equation, 1 over f is 1 over u plus 1 over v. Calculate that for the 3 values of u and v in the table, and then take a mean of the focal lengths you get. So for set 1, I get a 1 over 15 added to 1 over 32.2, which gives me 0.0977, and then if I take 1 over that, I get an f value of 10.23 centimeters. So you do that again for set 2 and set 3, and you get 2 other values. And if you follow that through, you get this value, and then we need to take the mean of these 3 for our final answer. So you get a mean value of 10.2 with 6's repeating, and since we only had 3 significant figures at best, we could write that down as 10.3. Part 4, state the principle of superposition. Well, remember that superposition is what happens when 2 waves share the same piece of space, and we get a net displacement that is coming from the displacements present in each of the waves. So we say that when two waves meet, that the displacement at that location is the vector sum of the individual displacements of the two waves at that location. Part B then, figure 4.1 shows two waves of the same type travelling in opposite directions that meet in the same medium at the same time. Give one reason why the two waves will not create a standing wave pattern. So we have these two waves. One's heading one way, one's heading the other way. And it says, why can't these two make a standing wave? Well, there's two reasons. One, they're not the same frequency. So these two waves would have to be able to meet each other at specific points and also manage to cancel. Remember, when we get a standing wave, we get nodes and antinodes. In order to create a node, the wave has to be able to cancel itself at a certain location, and that can only happen if they also have equal amplitudes. So part 2 then says, sketch the resultant wave that will be produced when the two waves meet. Remember that what we need to do is take the displacements belonging to one wave and add them on top of the other wave. So these are all positive displacements, so that's probably the easiest one to work with. We don't have to worry about the negatives. If we use this one, we only ever have to add the positives. So what we need to do is measure out these little displacements here. There's one like that. Whoa. One like that. One like that. Okay, so we're making out these little displacements. So what I need to do is add them. These are all positive, so I add them on top of the lighter coloured wave. So I add that on top here, and I add that on top here. You could do this with little arrows, which you then add to the other wave. This middle one is already operating from 0 here, so it stays where it is. These other ones need to come down. Again, they're always adding on top because these are all positive. Adding on top again, and adding on top again. And so there are two locations where the displacement of the dark line is 0, here and here. So those are points. And so basically the top of all of these is where my line has to go. So I'm going to end up with a line that something like this, going through the top of all of those displacements that I've added. This makes more sense if you use arrows rather than the rectangles I have used. The arrow tool on this explain everything is ridiculously big. So it works better if you use little arrows. Part C. The appearance of a standing wave as produced by a stretched string is shown in figure 4.2. How many nodes and antinodes are there in the standing wave of figure 4.2? Number of nodes, number of antinodes. So what you should really do is label out all the locations of nodes and all the locations of antinodes. So N's for nodes and A's for antinodes. So a node is a place of 0 displacement, and an antinode is a place of maximum displacement. So hopefully we can see there are 1, 2, 3, 4, 5, 6, 7 nodes, and 1, 2, 3, 4, 5, 6 antinodes. Okay, so part 2, the frequency of vibration of the string. To set up this standing wave is 70 Hz. The distance between two adjacent nodes is 15 centimeters. Calculate the lowest frequency of vibration that would set up a standing wave in this string. Well, we can hopefully see that that's one cycle. And according to this information, if the distance between two adjacent nodes is 15 centimeters, then the wavelength must be 30 centimeters. So we have a lambda value for this original setup of 30 centimeters. Now we have our wave equation that says that V equals F lambda. And so that'll give us the speed of waves in this system just by multiplying the 70 hertz by the 0.3 meters. So we get a speed of waves here to be 21 meters per second. Now the lowest vibration that can happen here would be the fundamental, which would be this kind of a wave where that's like lambda over 2. And we've already established, because if this is 0.3 from here to here, then there are 3 of those waves all the way across. So we have established that this distance here is like 0.9 of a meter, and that's equal to lambda over 2. So lambda for the lowest frequency is going to be 1.8 of a meter, and we use that with the speed of the waves of 21 meters per second to get a new frequency. So we've got a lambda of 1.8 meters, and V will still equal 21 meters per second. So F will be V over lambda. And that works out at 11.6 repeating, so we just round that up to 11.7 hertz. Okay. Question 5, figure 5.1 shows the pattern produced on a screen when a coherent light of wavelength 650 nanometers was directed towards a double slit. The distance between the two slits was 0.2 millimeters. What term describes the phenomenon that causes dark fringes to be formed? Okay, so when you get dark fringes using light, that's a peak meeting a trough, and that's what we call destructive interference. By taking suitable measurements from figure 5.1, determine an accurate value for the fringe spacing. Now this can't easily be done on the iPad because I now have a thing that's not the same scale as the original paper. So this will require you to go in here with a ruler and basically measure from, say, the edge of this one over to the far side of that one. Okay, I'm not doing this very well. Okay, something like that. And then we recognize that that corresponds to 1, 2, 3, 4 gaps. So the mark scheme says that your answer should be between about 6 and 7 millimeters, somewhere in that range. Okay, I found it to be about 26 millimeters between those 2 points on the printed version, and that gives me 6.5, which is in the ballpark for what they want. Okay, just ignore those lines. Calculate the distance from the slits to the screen. Okay, now we have an equation for this, and it's in the formula sheets. Is the lambda is AY over D. Distance to the screen is D here. A is the distance between your slits, and Y is your fringe spacing, and lambda is the wavelength of light being used. So top line, we've got 0.2 millimeters times 6.5 millimeters, 10 to the minus 3 for both of those. And we divide now by lambda, and we were told that that was 650 nanometers, 10 to the minus 9, and we just calculate that and find that it's 2 meters. Question 6a. The frequency of a pure note is played on a musical instrument can be determined using a cathode ray oscilloscope, or CRO. What other piece of apparatus is required to allow the frequency to be determined? Remember that a CRO is a voltage measuring device. Essentially, we need some kind of sensor that will convert sound into an electrical signal, and we call that a microphone. So sometimes the answer is staring you in the face and you're looking for something else. Just be aware, sometimes the answer is very straightforward. Describe what will be observed on the CRO screen and explain how this enables the frequency of the sound to be determined. So you need to explain that you're going to get a wave shape repeating itself on the screen, and that we can get time information by looking at how long it is across sideways on the scale. And the instrument will have a time base that is telling you that for every square this way is worth so many microseconds or milliseconds or whatever. So combining the time base setting with the screen measurement will give you a value for the period. And then you can get the frequency by doing 1 over the period. So like say for example the time base was 1 millisecond per square, and you were able to count how many squares it was across here. So if it's 4 squares, then that's like 4 milliseconds for one cycle, and that means that the period is 4 milliseconds, and so f is 1 over 4 times 10 to the minus 3. So once you've got the t value from making a measurement on the screen, looking at the time base setting, you can then convert it directly to a frequency. Part B. Explain what is meant by diffraction and state the condition required for maximum diffraction. And so we just explained that diffraction is the spreading out of waves after a gap like this or behind an obstacle. And the condition for maximum diffraction is the relationship between the wavelength and the gap size. So we explain that when the wavelength is similar to the gap size, you'll get maximum diffraction. Question 7a. What do the letters CT stand for in a CT scan? Well, this is just bookwork from your notes. The CT scan stands for computed tomography. State one similarity and one difference between the radiation used for producing a conventional X-ray and that used for carrying out a CT scan. Well, both of them use electromagnetic in the X-ray region. But since in a CT scan the X-rays are on for much longer, you're going to get a much larger dose getting a CT scan compared to taking a simple flash X-ray photography single shot. You imagine X-ray is like your camera flash going off and illuminating the scene, whereas the CT scan is more like having a video on for a period of time. So it's scanning for longer, so the X-rays have to be on for longer. So you're going to get a larger dose of X-rays with CT scan. Part C then. State one example of a person who would be unsuitable for diagnosis using CT scanning and explain why they would be unsuitable. Well, large dose of X-rays, you're thinking they're women during pregnancy, because obviously you've got an unborn baby there with a lot of developmental chemistry going on in its body, and ionizing radiation could interfere with that. So definitely pregnant women and the danger of harming the fetus. D then, what is the role of the computer in the production of the CT scan? And so what it does, it reconstructs all the slice information and puts it together into a 3D view. Question 8a, part 1. State what a photon is and describe how a photon can be produced by an electron within an atom. So the photon is the single unit of the electromagnetic radiation that we encounter. So we find that it comes in individual little bundles of energy, and we call those individual units photons. Okay, how do you get a photon? Well, you need an atom that is sitting with an electron in a higher energy level, and then that electron transitions down, and in the process of doing that, a little photon gets emitted. So an electron in an atom transitions from a higher to a lower energy level and emits a photon in the process of doing that. Part 2 then, most microscopes use photons of light to form an image. Light microscopes cannot get an image of objects that are smaller than the wavelength of the light that is used. Calculate the size of the smallest objects that can be seen with visible light photons of energy 4.97 times 10 to the minus 19 joules. So the first thing we're going to need to do is get a wavelength for these. So we have a photon energy equation equals HF. But in this case, we're interested in lambda, so we'd be better writing F as V over lambda. So the speed of light here is c, so V gets replaced by c. So hc over lambda is the equation we want to use. And that means that the lambda will be hc over E. And so we just need to fill that in and calculate it. So we've got H, which is Planck's constant, 6.6 times 10 to the minus 34. C, speed of light, 3 times 10 to the 8. And the energy we were given is 4.97 times 10 to the minus 19. And if we fill that in, we get a lambda of 3.98 times 10 to the minus 7 meters. Part 3. The visible light photons in Part 2 fall on an atom with an electron in an energy level of minus 4.23 eV, causing it to move to energy level B. So we've got this particle moving up to here, and that was caused by it absorbing a photon that was the same as the one in the previous part. And so that photon had 4.97 times 10 to the minus 19 joules of energy, and that means that level B is this amount of energy higher than this one. Now the problem is they're in different units here, so we need to convert this into electron volts and then add it to this to figure out what the electron volts are here. So to convert to electron volts, we need to take our 4.97 times 10 to the minus 19 and divide by the electron charge to get it into eV. So the value of the energy at B will be this 4.23 eV, the negative 4.23 eV, with this 3.11 eV added to it. And for that I get a value of 1.12 electron volts for the energy at level B. So the energy at level B is the energy the electron had before with the photon energy, this value here, added to it. So the electron had energy and the photon added more and brought it up to here. So the higher level is the minus 4.23 with the photon added, which gives us this new level. Okay, so we get 1.12 electron volts for that. B, part 1. Lasers have widespread uses in industry and medicine. State one medical use of lasers. So there's plenty of them. There's all sorts of skin treatments like tattoo removal, skin peels, those kind of things. We also use lasers for eye surgery to reshape the front of your eye to try and improve your vision. They're also used in keyhole surgery, where they're used as a cutting tool to make their way through things inside your body. So there's plenty of uses of lasers in medicine. 3 of the properties of laser light that make it useful is that it is coherent, monochromatic, and collimated. Explain what each of these terms means. Well, coherence all to do with the idea that the waves are all in phase with each other as they go along. Monochromatic is a single color. And that means that there'll be only one lambda present. And collimated is the idea that it's not diverging. You've got flat waves, and so you've got a non-diverging beam. Okay, which gives you like flat waves that are parallel to each other. Remember that if something's diverging, it's because the waves are curved. So the uniqueness of the laser is that it's very, very slightly diverging beam. There's very little divergence, and you can arrange for it to almost not diverge at all. Okay, so it's not diverging. They're in phase, and we've got a narrow beam that's not diverging. And monochromatic, mono meaning single, chroma referring to color. Question 9. According to wave-particle duality, electromagnetic radiation can either behave as a wave or as a particle. Describe the evidence which supports the dual nature of electromagnetic radiation. So, things like diffraction, interference, polarization, these are all things that we observe for light. But they're all wave properties. Okay, and the classic one for light as a particle is photoelectric effect. And the photoelectric effect is strictly a particle behavior because it's an energy interaction. So in the wave model, dim light has a low amplitude and bright light has a high amplitude. And the idea here is that energy is in the brightness of the light. But according to the photoelectric effect, the energy is coming in little packets. And those little packets have different amounts of energy. So a red photon has a small amount of energy, and a blue photon turns out to have a bigger amount of energy. So in the particle behavior, then energy is related to frequency. Whereas in the wave behavior, energy is related to like amplitude. And so the wave model basically says that if you keep increasing the brightness of a light, you're increasing the energy and you should get some photo emission. But it turns out that if you're below a certain threshold frequency, then you will not get photoelectric effect no matter how bright you make the light. And conversely, no matter how dim the light is, if you've got photons that have the right energy packet, in other words their frequency is high enough, you will start to get photoelectrons no matter how dim it is, as long as it's the right frequency. And so this is the trade-off between the two types. The photoelectric effect can only be explained if you understand light in terms of a particle that carries an energy packet related to its frequency, whereas wave properties say that energy is in the amplitude. Okay, so light displays lots of wave properties, but in the photoelectric effect it is displaying this particle behavior. And that's that.